In the last video, we built a container file system from scratch using rootfs, but there was a problem. Every container needed its own copy which doesn't scale. So the real question is, how do containers share the same base but still feel completely isolated? So instead of creating one again, let's open the real container and inspect what's actually happening inside. In this video, we are going to break down a running container file system live. You will see how files are layered, how changes are stored, and why containers don't actually copy an OS. And once you see it, we will build the same thing ourselves using the OverlayFS. By the end, you won't just use container, you will understand how they actually work. Now, before we test the terminal, I want you to build a mental model. Because if this clicks, everything else becomes obvious. So look at this diagram carefully. Here at the right hand side, we have one block called lower directory. So this represents your base image and it already contains files like file1.txt and config.txt. Now one important rule, we do not modify this layer and think of it like a read-only reference. Besides that, we have an upper directory. This is where all container changes go. Now understand this deeply. Modification goes here, creation goes here, and deletion recorded here. Now look at the top. This is a merged view. This is what the container sees, and this is the critical concept as well. There is no actual merge happening on the disk. This is computed at the runtime. So when a process asks, give me a config.txt, so OverlayFS checks the upper directory. If the file not found over there, it will check the lower directory. So merged view is a decision, not a copy. Now that you understand the architecture, let's build this ourselves. So let's go to our Linux terminal. So before we start, we need to check if the kernel supports OverlayFS or not. So for that, we can look for overlay in the proc filesystems file. So we can use grep overlay in the file /proc/filesystems. And if you see overlay printed over there, that means kernel supports OverlayFS. So now let's create a basic directory structure for today's demo. So first of all, I'm going to create one directory, mkdir overlay-demo. So the directory got created. Now let's go inside that. So right now this particular directory is empty. So let's create a couple of directories here. So mkdir lower directory, upper directory, working directory, and merged. So now I have created 4 directories in this and each has a specific role. So first of all, lower directory. It is a base image and it has a read-only reference. Then we have an upper directory that consists of changes made by the container. Then we have a working directory that is used for an internal workspace required by the kernel. And at last, we have a merged directory that is a final view seen by the process. So this structure is exactly how container file systems are organized internally. Now let's simulate a container image. So for that, I'm going to create a couple of files under the lower directory. So let's run the command that is echo hello from base image, and I'm going to create a file under lower directory with the name file1.txt. Similarly, I'm going to create another file under the lower directory that is echo config v1, and I'm going to store into lower directory with the name config.txt. And I'm going to create a subdirectory under the lower directory. So for that I can use mkdir lower directory and the data. So inside this particular data directory and I'm going to create one file as well. So echo data from lower, and inside this I'm going to store it under lower directory data and info.txt. ls the lower directory. So right now we created the files manually inside the lower directory. Think of this as a pull docker image, and this is our base image only, and it already contains application files and the configuration files. Now we connect everything using OverlayFS. So for that we are going to run a command that is mount -t overlay -o lower directory equal to lower directory, upper directory equal to upper directory. That is the directory name which we have created. Then comma working directory equal to working directory, and at last I am going to specify the merged. So let me explain this command very quickly. So -t overlay tells Linux we are using OverlayFS, and after that I am specifying multiple directories here. So here I am specifying the lower directory, that is a base layer, upper directory, that is a writable layer, working directory, that is required for the temporary workspace, and at last merged directory where the final view is exposed. So this command does not copy files, it creates a virtual file system view. This is exactly what Docker does internally. Let's press enter here. So OverlayFS created a mount point for this. So if I see that, so df-h, as we can see it got mounted properly, and here the file system is being used is overlay only. Now let's see what the container would see. So let's list the merged directory, ls merged. So if you see, something interesting happened here. So these files look like they exist inside this merge directory, but they are not physically copied. They are being read dynamically from the lower directory, and OverlayFS is deciding what to show. Now let's verify this step by step. First, check what the container sees. So for that, I'm going to cat the config.txt, cat merge config.txt. If you see, this is the same content which we have created under the config.txt inside lower directory. So this reads from the merged view and it should show the updated content only. Now let's check the original file. So if I run cat lower directory and the config.txt, if you see, this is the same content which we have placed under this particular file. So this reads directly from the base layer and this should remain unchanged as well. Now check what actually happened internally. And if I run ls upper directory, as of now, upper directory is empty because we didn't create any new file under the merge directory and we didn't modify anything. And that's why we are seeing upper directory as empty. But in lower directory, we have placed one file which is being used by the merge directory as well, because lower directory is a base layer for the merge directory. So OverlayFS copies first, then modifies. Now let's create a completely new file. So for that, I'm going to create one file under the merge directory. So echo new file and going to place under merged new.txt. So the file got created under merged. As we can see, the new.txt got created. And now if I run ls upper directory, so if you notice, new.txt got created here as well. And if I cat this upper directory new.txt, so if you notice, this is the same content which we placed under the merged directory with the file name new.txt. And if I run ls lower directory, so new.txt does not exist here. So that means it is being directly created under the upper directory. So upper directory is a writable layer and it contains the modification and the newly created files. So that's why we are able to see a new file created under the upper directory, and it does not update anything in the lower directory because it's a base layer and we don't place anything modified or newly created under the lower directory. So OverlayFS copies first, then modify. This is called the copy on write, and this is why containers are fast. They don't copy everything upfront. Now we enter the part where most people get confused, that is deletion. Because until now we added and modified files. But what happens when a container tries to delete a file that exists in the base layer? So we are not going to modify lower directory because it's a read only. So how do we remove something without actually deleting it? So let's see it in the action. So now let's delete a file from the merged view. So I'm going to delete one file, that is merged file1.txt. So before checking anything, remember this file exists in the lower directory, not in the upper directory. So now let's check what changed internally. If I run ls-l upper directory, as you can see, file1.txt appeared here, which is shown as a whiteout file. This is not a real file, this is only a whiteout file. So let me explain it with the help of diagram. So OverlayFS cannot delete the lower directory. So instead it creates a marker in the upper directory only. So this marker tells the system, hide this file from the final view. So that means deletion is not removal, it is just a masking. So the file still exists in the lower directory, but the container can no longer see it. So let me show you very quickly on the terminal. So as you can see, I have deleted the file1.txt in the merge directory. If I do ls here, so the file1.txt does not exist here. And if I list the upper directory, we can see the file1.txt as a whiteout file in the upper directory. But if I do ls in the lower directory, so the file1.txt still exists over there. And if I try to see the content for the same, I can still see the access for the file1.txt inside the lower directory, but it is being removed from the merge directory. So the same thing has been updated in the upper directory so that it can mark it as a whiteout file. Now let's combine everything and understand how the OverlayFS works internally. So this is the full picture of how container file system works. Let me break this step by step. At the very top, you see a merged view. This is what container actually see, and this is what your application interacts with. Now look at the files. We have a file1.txt, config.txt and the new.txt, and the config.txt is the one which is being modified. This looks like a normal file system, but it's not real. This view is computed, not stored one. Now move to the left side. This is the upper directory. This represents all changes made by the container, like the modified files, that is config.txt. So what happened internally for this particular file? So first of all, the file is copied from lower layer to the upper directory and then modified. And if you see, we have created one new file, that is a new.txt. So the newly created file is being directly placed under the upper directory. And if you see, there is one more deleted file, that is readme.txt. that is a whiteout file. Actually, it is not deleted, it's just hidden using the whiteout marker. So upper directory only contains the changes. Now look at the right hand side. These are the base image layers. So layer 2 having a multiple files like a shared, data bin, bash script and the readme.txt. And the layer 1 is having a 2 files, that is file1.txt and the config.txt. Each layer adds or modifies something, but no layer stores the full file system. So each layer stores only the difference. Now focus on the center arrow. This is the OverlayFS. This is where the magic happens. OverlayFS does not merge everything physically. It creates a logical stack of layers. So when a process asks for a file, first of all it will check the upper directory, then it checks the top layer, then it checks the next layer, continue to the downwards. So OverlayFS walks layer from top to bottom. Now everything we saw so far follows the simple rules. If a file exists in the upper directory, that version is always used. It does not matter what exists in the lower layers. So if a file is deleted, it is not removed from the lower layers, but it is hidden using a whiteout. Third, copy only when needed. So files are not copied by default. They are copied only when modified. So upper layer always wins in these scenarios. So now let's connect everything we built. Lower directory having a base image layers, upper directory contains the container changes and the merged view what the process sees, and OverlayFS is the system deciding which version to show. So container don't have their own file system, they have their own view of the file system. Now everything we just understood is not theory. This is exactly what your container runtime is doing every single day. So let's go back to our terminal and let me clear out the screen first. Now before we build anything, let's inspect a real container. So for that, let me create one container using Podman in this. Podman run -d -name my nginx and the nginx image. So here I'm going to create one container with an nginx image and I'm giving a name that is my nginx. And -d, it creates a container at the background. So let's press enter. So the container got created. Let's run podman ps command here. So here we can see the container is listed and the container ID is this one and the image is being used, that is nginx, and the name is my nginx. Now let's inspect how this container is built internally. For that I am going to use a podman inspect command. So I can use podman inspect container ID. And then I'm going to look for some specific data for the graph driver. So JQ, and here I'm going for .graph.driver.data. So let me explain this command very quickly. So podman inspect and the container ID gives full container metadata. And at last I have used graph driver.data. It shows the file system details, and I have used JQ to format output so it becomes readable. So let's press enter. As we can see, we are getting an output in a similar way which we have created our directory structure. So let me decode it step by step. So first of all, we have a lower directory and it has multiple layers internally. Basically, this is not a single directory. These are the multiple layers stacked together. So each path here is equivalent to one image layer. This is exactly what we saw in the diagram. So lower directory has all image layers stacked together. Now one important detail here. Order matters a lot. First path is a top layer, last path is a base layer. So OverlayFS walks these layers from top to bottom. Now look for the upper directory. This is a single directory if you see here, and this is also the container's writable layer. Every changes we made earlier manually exist here in the real containers. So upper layer contains the container changes only. Now look for the merge directory, and this is where the final file system is exposed. When your container runs, this is what it actually sees. So lower directory has a image layers, upper directory has a container changes, and merge directory what container sees. So we build this manually, but Podman or Docker just does it automatically. Now I want to show you something that most tutorials skip. We are going to create a container but without Docker, without Podman, just using Linux primitives. So before we run anything, understand the container reads isolated file system, isolated processes, isolated network. So first of all, let's create a container using the unshare command. So let me clear out the screen first, and I'm going to use a unshare command -mount -uts -ipc -net -pid -fork and -mount -proc and the bash. So let's press enter here. Now we are inside this shell, and if I run echo $, we can see the PID 1. Now we attach our layered file system here. So for that I'm going to use mount -t overlay and the same directory structure which we used. So lower directory equal to lower directory, upper directory equal to upper directory, and working directory equal to work directory, and at last /mnt. So let me explain this command very quickly. This is the same command we used earlier, but now we are inside an isolated environment. So this becomes our container file system. So let's press enter here. I think I did one typo here. So let's update the same. Instead of lower directory, I just typed lower only, and let's press enter here. It worked successfully this time because earlier I gave a wrong parameter, that is lower, and it should be lower directory. So let's verify the same. So df-h. So now look at this carefully. You will see a new entry for /mnt, and notice the file system here, that is overlay. So that means /mnt is not a normal directory. It is mounted OverlayFS file system. Just a moment ago, /mnt didn't exist as a file system. But after running the mount command, it became a completely new file system layer. So we didn't create files, we created a new view backed by the OverlayFS, and Linux treats it like any other file system, which is why it shows up in the df-h command as well. And this is exactly how containers get their file system, a mounted overlay, not a copied disk. And here if you notice the size, that is 100 GB. So this size is coming from the underlying file system. OverlayFS itself doesn't store data permanently. It just uses the underlying file system. So now let's move under the /mnt drive. So cd/mnt, and if I do ls here, so this directory is not your container root file system. It is isolated, layered and dynamic. And if you notice, this is the same files which we have placed under the lower directory, which is being placed in the /mnt as well. And if I run pwd here, so this is our /mnt only. So we just build a container from scratch. Namespaces plus OverlayFS, that's a container. Now let's prove why containers are efficient. Let me clear out the screen. So for that I'm going to use a du command, and let me go to the root directory first. And here we have a overlay demo. So if I run, so now I'm inside the overlay demo directory, and if I run du-sh lower directory and the upper directory. So here du-sh shows a disk usage. If you notice, lower directory is having a large space, that is a base image, and upper directory is a smaller, it only having a changes. Now connect this to a real system. When you run 100 container, they all share same lower directory. Only upper directory changes per container. This is why containers are lightweight. Now you don't just use container, you understand how they work, how files are shared, how changes are isolated without copying the base image. But one piece is still missing. Container don't just use layered file system, they replace the root entirely. And that's where pivot root comes in. In the next video, we will break that down. If you found this video helpful, hit like, share it with your friends, and subscribe for more content like this. Thanks for watching. I will see you in the next one.